All right, so let's go ahead and get started. For my announcement today, the tech club that I mentioned is planning on having a meeting this coming Tuesday at 5:30 p.m. at a location to be determined. I'll let you know as soon as I have that information, so probably on Tuesday. That's the plan. The idea for Tech Club is that we're going to have probably monthly events where we get together and do something like maybe leak code problems, practice for interviews, be in community with other tech enthusiasts. We're also planning maybe having like a panel of former students come and talk about their experiences in industry, and maybe also having a hackathon, like a mini hackathon, sometime near the end of the semester. So if that's something you're interested in, I encourage you to come to this when I give you all the correct details. My plan for today is we're gonna most likely finish the math background section. For those of you in 485, I've changed this a little bit, so we'll do slightly different examples. That way it's not dreadfully boring. And we'll go through some of the proofs in the packet in class. We'll do different ones than we did this morning. Yeah, that's the idea. If we finish that, we will start chapter 2. If that's the case, I'm planning to post homework 3 on Tuesday. So that will be available. Let me just show you what Canvas looks like now. Because I made some changes during my lunch hour, there's a new PowerPoint that has slightly different examples near the end. Everything else is pretty much the same. And then I've added the new unit as well. Okay. Any questions before we get started? Great. All right, so last time we were talking about set theory mainly, right? How we looked at the union of two sets. We looked at the difference, or one set minus another. We looked at the intersection of two sets. We looked at the complement of sets. And we saw how you can combine these to make something that are interesting. You can combine them to get all of these different configurations. Now we have like a slight detour where I talk to you about Boolean operators. Has anyone taken like a computer systems class? Do you remember like logic gates? Yeah, so this is kind of like that. This is mostly just like, I would like to mention it because I think this is really cool. Especially how with logic gates, you can come up with pretty much every implementation. Like you can come up with an if statement and a for loop and like complicated processes just by using these simple operators. So I think that's so cool. So I just want to mention that. You're probably familiar with the operators like and, or, and not. We use these in programming all the time. Things you may not be familiar with are the like NAND and NOR, or XOR or XNOR. Again, I don't want to get too much into detail, but these are just operators that you may not have heard of before, where NAND is true unless A and B are both true. So otherwise, if A and B are both true, then NAND is false. NOR is only going to be true if neither A nor B is true. So if A and B are false, then NOR is true. XOR is if you go to a party and someone asks, would you like a hot dog or a hamburger? And in the mathematical or, you could just say yes and expect both if you would like both a hot dog and a hamburger. But typically that's kind of framed as an exclusive question, right? You either get a hot dog or you get a hamburger. And so XOR fills that gap with that logical operator where XOR is true only if only one of them is true. And then XNOR is true only if they have the same value. So either only if they're both true or if they're both false. And this is a fun picture that I enjoy to kind of show like what this is meaning. So like trick or treat, we know what that is. Trick and treat, we've seen that before. XOR is only true for one or the other, but not both. NOR is true outside of that, and so on. So I'm going to leave the truth tables to you. If they're also on the internet. Wikipedia has a fairly good description of truth tables. So I'll leave that to you for the homework. But we're going to talk about different kinds of proofs. So we've already kind of discussed this a little bit. We talked a little bit about induction, a little bit about contrapositive. But we'll look at them again. So one of the things to remember, especially as we look at some elementary proofs, if you've taken discrete math, this probably sounds familiar to you. One of the things, if we're working with integers and looking at like even numbers or odd numbers or things that are divisible by 2 or some other number, we tend to use algebra here. So we'll use a variable, I'll call it n. It could be whatever we want. It could be a, b, x, y, z, so on. So for the first proof we're going to do, we're looking where n is some number and we assume that it's an integer. That's one of the important things, is to make sure we know what we're assuming. This will come in handy for especially the dividing by 0, which some of the people in the earlier class saw. So the way that we represent an even number in proofs is by 2 times something, where it makes sense because like if I have a number 8, you can factor a 2 out of that. 8 is just 2 times 4, right? So we can pull that 2 out. And that's kind of the way how we write this here. 2 times something. We don't necessarily care what the something is, just that it's has a factor of 2. And then from there, we can come up with an odd number where, as you know, so if I have a number 2 that's odd, or let's start a different number. Let's start at 8. 8 is even. 9 is odd. 10 is even. 11 is odd. It switches. Every number is either even or it's odd. And so since we know how to write even numbers, we can express an odd number as there's just an even number plus 1. And again, where we're assuming that number is an integer. Okay. So the intro proofs, which I think is one of the hacker problems as well. Yeah. Which is to prove that the sum of 2 odd numbers is odd. So let's think it through and then we'll add some words to make it a more formal proof. So we want to prove that the sum of 2 odd numbers is odd. And so we start with, what do we start with? Yeah.
Let n equal 2a plus 1 and let n equal 2b plus 1.
M, did you say?
Yeah.
Sure.
M's good.
Or, no, sorry, I didn't hear what you said.
Oh, m, yeah. Let m be 2b plus 1.
Yeah. Great. So now we've got 2 odd numbers. That's our starting place. And then what do we do? We're trying to prove the sum of them is odd, so let's add them together. So n plus m is 2a plus 1 plus 2b plus 1. We can simplify this, right? So 2a plus 2b plus 2. What do we know about this? Yeah, we can factor out a 2. They've all got 2's in here. 2 times a plus b plus 1. Wait, did I do it wrong? Yeah. Yeah. Right. You are correct. The statement is false. I made a mistake. So this is a good example of a proof by contradiction, right? Where we said the sum of two odd numbers is odd. And so we're looking for an odd number here and we didn't find it. Do you have a comment, Jude?
So yeah.
Yeah. Right. Okay, so I'm not giving the answer away. Great. Yeah, so if we're proving it that it's even, hooray, we found an even number. Great job, us. Yeah, so on a proof, you can, I mean, I feel like this is fairly clear since it's a fairly simple problem. If you want to be thorough about it, we can add words. So we could say like adding together n plus m equals this, and then we could say we're going to factor 2 out, and then we get this. So basically adding a word or two to kind of explain, here's the next math step that we did. And then we say, which is divisible by 2. Therefore, we're done. Typically end our proofs with like a little square or QED, which means something in Latin. Any questions on this? Cool. I love it when I go through something and like I did something wrong here. Okay. So I would, let me see. So I want us to do 7B, the second one in 7, and then the fourth one in 7. And I brought markers, so if you want to talk about it with your neighbors and then put it up on the board, you can choose either one or the other. Yeah, question?
For 7A, since it's written as prove the product of two odd numbers, should we prove that for the product, or do we just do the sum like what was
Stick with the product. I'm reasonably confident that the product of two odd numbers is odd, right? 3 times 3 is 9. Okay. All right, so I've got my markers. Do I have the packet up here somewhere? No, I do not. Math background, I do. Okay, so work on either the second or the fourth.
Some for a second one.
Hold on a second.
For the second one, proving this is squared, every square thing's awesome. You know, that, is this
Square of an odd number is odd. Yeah, that's the correct approach.
Like writing a square, even though I know I'm looking at this, it's perfect. I did this square. Yes. Yes. Anyway. Anyway.
All right. I would actually like to go over the days of the week one. So make sure you take, so, because part of the package is also your homework, so if you're working on other things, work on those later. But let's look at the days of the week one. So if you haven't discussed that in your groups, go ahead and start to discuss it now. If you have discussed it, throw something up on the board.
Is your first? I mean, since you understood. Oh, that, unfortunately. You know, no, we'll be in the same. So, Thursday. Yeah. No, I did that. I mean, not there. It's 70 or it's 8. It's 8. Look at you. We go. Yes. If you want to, so you're counting Tuesday. So Tuesday,
Okay.
Tuesday to Tuesday,
Yeah.
Tuesday to Sunday. I mean, I have to fight my own thing. You can't just, okay. It's okay. Okay, so if you could just disprove this one thing that I'm, so like, we can just, they can.
When you take out there, you count it. You count that same next week, or do you skip to the next day?
You just say Tuesday to Tuesday instead.
Tuesday, 7 to 8.
That's what I'm saying. That's what I'm saying, yo. Guys, okay, cause these actually is 8 days, so my thought, I was watching, keep saying 9, it's technically 8. How are there 8 days? It's not 8 days, it's Tuesday. We're not. Okay. Yeah, I'm gonna write. Well, that 2 plus 2 days. Equals. So then in 90 days. Equals Thursday, so then another 90 days, 99 days will be Thursday. Yeah. I would send. Right. Do you think it's? I'm going. Nine.
We did the one.
So-
Before this one, where like anything.
In 90 days.
It's a report. Yeah, many algebras.
We just wanted. That one explain. When you divide the number.
Great to me.
Yeah. Monday's one, Wednesday, Thursday.
Yeah, I fucked it. We can't do. We can't.
It's still not clear to me. Why? How do we get from?
I don't think it actually.
Let us add. Sign.
Who knows what that's what you have to find.
That's very interesting. Okay, so we'll let these people finish up.
That was, that was
All right, if you're still writing, go ahead and finish up. I will summarize what I'm seeing. So first of all, back here, we've got a day of the week, logic, which is interesting. So assuming the day of the week, so you're assuming the week starts on Monday, right? I always think it's interesting how like for me, the day of the week starts on Sunday. Like Sunday is the start of the week. And I feel like Monday starting the week is just like completely different worldview. This is a tangent. I just think that's interesting to think about. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. So you're assuming Monday is day 1 and Sunday is day 7. Okay. So your reasoning is Tuesday is day 2. And so 2 plus 100 gives us 102. And then we divide that by 7 and look at the remainder. That's 4. And this gives us the day of week. So 102 mod 7 gives us Thursday. Yeah, that's fair. There's another, I see kind of 3 examples of this, maybe 4. 4.5. Where the idea is that so a week is 7 days. Week is 7 days. And so if we divide 100 by 7, we get 14 remainder 2. So we get 2 as the result of the modulus. And so if today is day n, then however many days we're looking for, we just divide that by 7, look at the remainder, and that gives us n plus 2. And since 2 days from Tuesday is Thursday, then this is Thursday. And we can do that for like 3,004 days since Sunday. So 3,000, someone pull out a calculator. 3,000 divided by 3,004 divided by 7 is 429. Oof. Yeah, answer. Remainder 1. Great. Saves me from having to do long division. So yeah, so since we get remainder 1, that way we know that 3,004 days since Sunday is a Monday. So that's another way to approach it. I also see like the days, the number of weeks since Tuesday, which is kind of a similar prospect where you break 100 into the yeah, you get 14 remainder two as well, where you break 100 into number of weeks and then just leftover days. And then over here, we've got some algebra. We got 7n plus 2 equals 100. So you have the like the n plus 2 thing that I'm thinking about. Why do you have 7n? Okay.
And then if you add 2 more days.
Right, and you're trying to prove, I would say that I wouldn't assume that the left-hand side equals the right-hand side. That's kind of what we're trying to prove. Yeah, sorry, my brain is catching up. Yeah, so if you were to write this on the like the homework or on an exam, I think I would require more words. Like obviously like it's just something you put up on the board, but in general, like having more words and not just math helps me to understand it. And also if you ever go back and you're like, hey, how did I do this? Having the words there to explain it is will help convince you that like your argument is right, and it will also convince me. Okay, thank you for participating. That was really interesting. You came up with things that I didn't think you would, so that's awesome. Okay, so now we'll talk about the proof techniques. So there's 4 main ones that I can think of. One of them is direct, which we've been pretty much doing, where we start at A and we reason our way to point B. So that's like the sum of 2 odd numbers. We get to a point where we're like, this is clearly even, we're done. That's A and B, or A to B. Contrapositive is where, if you are familiar with Boolean logic, so this is the statement, but if a way to reframe the statement that is also true is to say not B implies not A. So one of the examples that I've seen is if it snows, then they will cancel school. And so one of the things we could assume is that the way that we do this with contrapositive, if they didn't cancel school, then it hasn't snowed, right? That's an example of a contrapositive statement. And so the idea is we start with not B, and then we work our way to not A, but the style is like a direct proof. This is a little bit different from contradiction. So for contrapositive, we're looking just at the right-hand side and we're assuming that's not the case. And then we're working our way to the left-hand side. Contradiction is different, where we assume that the whole hypothesis is crazy. And we say, this as a whole cannot be true. And then we look at the implications of that, of what's the fallout from that decision. Do you see how those two are different? They're like, they've both got contra in them, where we're assuming not something, but they work slightly different. And then we've discussed induction previously as well, where we start with the base case and then we assume works up to some value, finite value, and then we prove one after that. Okay, that's the problem 8, just filling in those. I have an example for contradiction. Does anyone need more time for this? Seeing none, let's move on. Okay. I would like to prove that there are infinitely many prime numbers. So the people in 485 got that the square root of 2 is irrational. You guys get that there are infinitely many prime numbers. Professor Sauerberg, when I took his Math 103, which is what it was called then, I think, told me, like the whole class, that if I see you on the street 20 years from now, I expect you to know how to prove that the square root of 2 is irrational, how to prove that there are infinitely many prime numbers. I'm not going to expect that of you. I would encourage it, however, because I think it's cool. But then again, I turned out to be a teacher, so. Okay, so we want to prove that there are infinitely many prime numbers. Remember, a prime number is a number that, what? Divisible only by itself and 1, right? So there is also a theorem we can cite that a number has prime, and like any number is divisible by a prime factor, right? So either the number itself is prime, so like for 3, the 3 itself is prime, but for 8, it has a prime factor of 3 2s, right? So from any number, we can get its prime factors. 2 assumptions to work into that we will use going into this. Okay, so we want to prove this by contradiction. So we're assuming that the hypothesis is crazy. That means that there can't be infinitely many prime numbers. Therefore, there has to be a finite amount of prime numbers. Like we can list them all. So the way, I have to think about putting these slides in LaTeX because PowerPoint math, I'm not a fan. Anyway, that's something for next time. So we'll write numbers usually with subscripts to identify them. So like P1 is the first prime, which is 2, and then P2, and so on until we get to prime number n, which is at the sum point where there stops being prime numbers, right? N is finite. It's got to stop sometime. That's what we just assumed. So just for fun, let's multiply them all together and add 1. And then we want to see what the result of that is. So if we multiply them all together and we call this number n, so all of these primes that we have listed, we just multiply and then add 1, and we call that number n. Here are some things we know about n. Since we've listed all the primes, and n is a product of primes plus 1, n's got to be bigger than any prime. We've listed all of the primes. We know what they all are. It's got to be bigger than those, any of them. And the other one is we know that n cannot be prime because we've already listed all the prime numbers. With me so far? Okay, so we're going to look at the implications of the second one, where we say that n cannot be prime. If n's not prime, then it's got a divisor, right? Because a prime number is only divisible by itself and 1. If n's not prime, then there's some divisor. And moreover, n has got to have a prime divisor because that's how numbers work. So it has to have a prime divisor. So thinking about which one could it be, because we know all the prime numbers. But we can't. It can't be that. The reason is because, so here's where a contradiction lies. So n has to have a prime divisor. And it's got to be one of these. But it can't be any of them because we've multiplied them all together and added 1. And so because we added 1, that means it's not divisible by any of them. That's where we get the contradiction. So yeah, so it's the idea of knowing that this number has to have a divisor and then going through the consequences of what that means. Once we get to these 2 steps, which both must be true and both cannot be true, then that's our contradiction. So once we reach the contradiction, then we just state, therefore, there must be infinitely many primes. Any questions on that? Cool. Do I want to do any of the ones on number 9? I think I'll leave number 9 for you to do outside of class. I would like to do let's go through induction and then I'll have you do 10 and whatever number 11 one. So we've talked about induction, the idea where we start with a base case, assume it works up to some number, and then show it works for 1 more. That's the basic structure of induction. I'm going to do an example, and to do that example, I would like you to remember the rules of exponents, where something to the 0th exponent is 1. If you have something with the same base and you multiply them together, then the exponents get added. If you have one number over another, the exponents get subtracted, top over the bottom. And then if you raise something to a power, that gets multiplied. And then if you have something times something to an exponent, the exponent goes to everything in that group. And then the negative exponent is just 1 over that. So this one and this one are what we'll use in the proof. I just wanted to remind you of those because it may have been a while. Okay. I don't have any words for this, so we're just drawing it. Okay, so I would like to prove that 2 to the power of 2n, 2 times n, minus 1 is divisible by 3. That's what I'd like to show. So just to note the divisible by 3, remember when we were working with like 2n? So let's say divisible by 3 means we can represent it by 3 times some number. For m, I'll say m is in the natural numbers. I always mess this one up. It's a weird Blackboard n. Basically means the set of natural numbers, which is 0, and then 1, and 2, and so on. So basically not negative. Okay. So we can write a divisible by 3. That's what we're looking for, where we can pull 3 out of something. Okay, for induction, we start with a base case, where we say, let's look at the simplest possible examples. For natural numbers, the simplest possible example is 0. And so what happens when we plug 0 into this? We get 2 to the 0 minus 1. 2 to the 0 is 1. We get 0. Is this divisible by 3? I would argue yes, technically. We can say 3 times 0, where m is 0. Great, that works fine. For just to assure ourselves, let's look at n is 1 and 2. 2 to the 2 times 1 minus 1 is 2 to the 2 minus 1. 2 squared is 4. 4 minus 1 is 3. Is 3 divisible by 3? Yeah, by definition. Okay, that's supposed to be 2. So technically 0 is enough to move forward, but I just want to convince us for introduction examples. So 2 to the 2 times 2 minus 1 is 2 to the 4 minus 1. I didn't do this one in my notes. 2 to the 4 is 16. Nope, that's 2. Wait, it is. Sorry, I'm doubting myself. 16 minus 1. 15 is 15 divisible by 3. 3 times 5. Check. Great. Our base case is done. It was done a while ago, but now it's extra done. Okay. So we've assured that the base case works. Now comes the induction hypothesis. For the induction hypothesis, let's say that we call this, I don't know, P for premise, N. So we want to show that, so if we say this function, we call it Pn, we want to show that P of K implies P of K plus 1. And so to do that, so we want to prove K plus 1. That's the idea. To do that, we're going to assume that the premise at K holds, right? So what does premise at K mean? 2 to the 2K minus 1 equals something like 3m, right? So we're assuming that both sides of the equal sign hold. So let's look at, we're going to look at the left-hand side of the equal sign with K plus 1. I'm going to rewrite this on the next slide. So premise at K is that 2 to the 2K minus 1 equals 3m. And so if instead of K, we substitute K plus 1. So P at K plus 1 is 2 to the 2 times K plus 1 minus 1. That's what we're starting with. We're working on the left-hand side of the equal sign. We don't know what the right-hand side of the equal sign is yet. We haven't proven that it's anything yet. Okay, so let's FOIL this out. Or distribute this. 2 to the 2K plus 2 minus 1. And then from there, we can separate the exponents, right? Because we have exponent rules where we've got plus, then we can make it 2 times something times 2 times something. So we get 2 times 2K, or not plus, times 2 minus 1. And then we get to 4 times 2 to the 2K minus 1. That's where we kind of stall out. So the idea is, this is where it kind of gets complicated. So we've got a 4 here. It would be really great if we could factor out a 4. We can do that with a little bit of sneakiness. So remember, the left-hand side of something, like without an equal sign, we've only got an expression, right? It's not equal to anything yet. So if we want to do any arithmetic, if we had an equation, you just do it to both sides. And it's like as long as you do it to both sides, then you're not changing it in any real way. For an expression, which is only one side of the equal sign, we have to, if we're gonna add anything, we have to add it and remove it at the same time. That way, it's net zero. So the thing we're gonna do is we're going to add +4 and -4, because we want to factor out a 4. So if we simplified all the constants right now, it would just get us back to what we have now, right? So I hope that assures you that we've done nothing. It's just here to help us out. Okay, so let's rewrite this a little bit. So 4 times 2 to the 2k. I'll move the -4 up front. And then I've got a -1 and a +4. Good news, with those two terms, I can pull out a 4. And so this is where it's a little bit sneaky because we know that we're looking for something -1, I chose the -4 because I know if I pull the 4 out, that's going to give me -1. If I had used +4, it would have given me +1, which is not what I want. So we've got that, and then we can't forget the stuff that's left over, which is just +3. If we were to FOIL this out, the +4 and -4 would go away. Okay, let me rewrite this last step, unless anyone needs more time. I'll give you a second. I'll also post the slides on Canvas at the end of the day. Remember, all this math is us doing that induction step. If we're trying to prove k+1. This is all our work that's where the bulk of the work in induction comes in. Okay, so I'm rewriting 4 times 2 to the 2k -1 +3. Yes. Okay, so good news, we've reached a place where we can use our induction hypothesis. Remember, our induction hypothesis is this whole equal sign, this whole equation, right? 2 to the 2k -1 is equal to 3 times m. Look right here, we found it, we made it. So let's substitute that. We've got 4 times 3m +3. And then, now we just redistribute the 4. That gives us 12m +3, which gives us 3 times 4m +1. Is this thing divisible by 3? Yeah, there's a 3 right there. We did it. Hooray. So we've gotten to a place where 2 to the 2k +1 -1, going all the way back to our initial question mark over here. We've gotten to a space where this equals that. Therefore, by induction, we've done it. Hooray. So we've gotten to a space where we can say that for any value of n, this number is going to be divisible by 3. So induction is really good for when you don't know how big something's going to be. It's useful for graph algorithms in particular, and other things like sequences where we start at one space and then show far off down the line, this still holds for some arbitrary number. Any questions on that? Okay, so the induction questions on the packet slash homework are very much less mathy than this. I just wanted to show you like what induction proof with math looks like. So for the packet, I hope that you kind of keep the rigor of here's how induction works, but just use more words and apply it. In case you're interested, there's a sheet of paper pinned up in the math lounge that I think I'm like 98% confident that I wrote when I was a student. That just shows a silly little story of someone inviting someone into a house by induction, where we start with the base case of like your feet are on the floor, so that's great. Then we have an induction hypothesis where we say, however tall you are, let's just suppose we cap it somewhere, and let's assume that you can fit through the doorway. And then the bulk of the work is n+1, where we say, if you're at least 1 foot taller than that, you can at least crouch until you get to the dining room. Therefore, you can come in the house. That's the idea of induction. So it's 2:35. I think I would like, let's see so we end at 3:10. I want to have us work on problem 10, which is when written out in English, every odd number has an E in it. So I would like us to discuss that. I think that is a fun one. And here I wrote down 11A, but I actually want to see what you do with the chocolate problem. So at least to get you started on that. And I'll give you at least till 2:45. And then maybe we'll start the next chapter. So problem 10 and the chocolate problem. One by seven. Ready.
It's,
Yeah, no.
That's what I want you to do, yes. Don't drop it.
Yeah, I think like most, you can just say, just. Yeah. Right.
Yeah, I'm on the right. I'm so like. I break it down.
yeah.
And I think what you're doing, they feel like
No, inquiry out, he does.
So have your number with this. Abstract.
You should go. So you can do a remote play, bro. I sit on my console favorites. I gotta.
For the induction set, if I had more. Okay, well, maybe I'll go to that. One side is J and one side is K. They both go in C. Those lines K, or they can be different. Right.
They can't.
So then for my induction set, should I go with J and K by?
No, you're not kidding, no. What house do I find that out? What time you have? Marvel, that's a game to pop on. I tried that.
I think it would have been to add both. Try different ways, like sketch it out to yourself, what if you add both? If you only add one or the other.
Okay.
That's just a question.
So, yeah.
It's like three cases, the
That's
inside
good.
is 0, it's one, and then inside. So if it works for, when it's a base, then it's. You got each one works.
Technically, the second one on problem 11 should be only $1 or $5 bills. Because you are probably not able to get some numbers by $1 and $5 bills. Anyway. Small correction. It may change the meaning of the problem. Okay, does anybody have a good proof for every odd number has an E in it? If you do, go ahead and write it up on the board. Otherwise, continue the chocolate thoughts.
I don't know. Yeah. No, you do that, you do for us. Oh, it's great. And then he's like, here's the deal, and I'm like,
Yes, there we are.
oh, okay, that's my, I'm talking about. Yeah. I'll sing your message. He never said anything. Yeah, he never said what's the formula. He literally said like things.
Well, I would say you really wanted to say this because you could increment one time and then.
For some reason. It's actually not. Okay.
He needs to.
I'm sorry. I come out aggressive. Oh, wow, thanks.
Plus N.
Like, it doesn't take much.
Right now,
Did you check out the sources?
No.
You actually got it? You know, I was doing the memory management sequence. I would just ask.
So the idea is a break. A break. So Like,
If you-
then repeat that to you. Yeah, so that equation is different. But.
Yeah, I'll do something.
You got like 75. And so.
I was gonna implement all at the same time, but then they would say.
And then. Yeah, I think it.
Yeah.
J. Oh, 7 times 3. Yeah.
Could you,
Yeah.
could you argue, it's probably not sufficient, but could you argue that if
And
you,
so then you can just write.
if you're proving by induction for one side, you can successfully increment one side, is that equivalent to then increment the other? Because- Right.
And so.
Sorry. You don't got it on your last day.
That's not like the day with the without. And then.
Chat.
That basically decides length line and height line. But in either of these.
Yeah.
What if you increase both at once?
The Reagan part.
Yeah. Without loss of generality is, if I chose to assign n to the 4 and m to 7, I could have chosen different. And it would give me,
And then
like, without loss of generality, it would give me yeah.
there is.
So the generality is what's the orientation of the topic? Yes, we still have to prove.
Yeah.
A plus 1, or whatever variable, and both. A plus 1 and. Right, so the generality comes in saying this is, draw, please. The generality is saying this is n and this is m. I could have said this is m and this is n. That's the without loss of generality of I have to assign n and m to a side. So I'm just going to pick one. But since they're generic terms, I could have chosen either one. That's the only generality that we can kind of throw away with this. We have to consider the other cases.
Okay. So like whenever we say like without loss of generality, like ever, does that mean like I can input variables that we have, like, no matter how they're switched up, doesn't matter.
I think that's the general idea, yes. So when there's some sort of choice to be made, as long as okay, so as you're going, so you've come up with some equation, right? In terms of m and n, that you say that this equation works for all cases. I won't give it away. But you end up having to prove, so let's say let's say the induction hypothesis is J and K, right? So we just rewrite this equation in terms of J and K for M and N respectively. Keeping that respectiveness is important. That's the generality that we were working with before. We like made a decision and we stick with that decision. The tricky thing that I didn't anticipate for this problem, but is absolutely correct, is that if we just had one variable, so like for this one, 2 to the 2n minus 1, we only have one variable. And so we only need to test for k plus 1. But for this, we've got two variables. And so there's 3 possibilities here for the adding 1. So one of which is j plus 1 and keep k as it is. The other is keep j as it is and do k plus 1. And the other is j plus 1 and k plus 1. Yeah, so that's the goal. All right, continue talking.
No.
I'm gonna go around and make sure that you all have the correct equation. Breaking this column first. And then, so you're left with m columns. Then you need to break each column n times. So you have some n, or wait, no.
You talked about that. No, it's hackers.
And how many, so break each column by m minus 1 time. How many times total will you break columns? How many columns are trying Yeah.
Other places.
First introduction.
Yeah, I would assume the base case, so 2 is fine, or 1 also. Instead of
I think it's
1
like
down.
credits. It's not right. Correct.
You can also include 2.
Yeah, I don't know, I mean. I think it's very well.
There's a lot of important, like, assumptions.
Technically, you know, have to tell mass to talk about dimensions, we like about it.
Yeah.
It's not as a pattern, and switch, that's what it goes with I want to talk about. Yeah, because I think I should break rows first. And then row column first, and then bring. Yeah, I don't, equation first. What's your, you have an equation?
Yeah. Yeah.
So, like. So how many breaks, it's a break columns. How many breaks? I think it's which is M. Length of 7, probably bar breaks. Or length of M, probably bar will break.
Okay, so you have that.
Six.
Oh, we get one thing. You got it. Finish three. Finish your answer.
M minus 1. 7 is 6, as M is M minus 1. So break into columns first, made M minus 1.
Did you do the
Now you need to break
ID?
all of these. Yeah,
Bubble?
so for this chocolate bar, how many did one column take? One, two, three. And so three and five, so. This is N.
Oh, well, your hearts.
So N is this is four.
There's that house or practice. Oh, I did.
We have one less break than the length of the bar.
No, they did that, it's like, okay, it's compounded.
Simpler than you think. Simpler than you think, I guarantee you. You have a height 4 chocolate bar that make these breaks. You have a height 5 chocolate bar, you make 4 breaks. You have a height 10 chocolate bar, you make 9
Yeah,
breaks.
32 for the year, or no, yes, yeah, yeah.
Yeah. So that's to isolate each of the individual for one column. How many times are we gonna use that process? Six. No, how many columns do you have? Those are already broken, already broken.
Oh, you're saying the same.
Yeah, so we've already broken them into columns. Now we need to break them like top down.
Oh, cool.
Right, so that's the N minus three top down. So, yeah, so let's say I've got like find 7 individual columns. I know it takes 3 breaks to break each
Oh,
column.
this one.
So I'm gonna break all of the columns. I'm gonna do that. So. So I've got like. Right? So to break it into these columns took me, let's see, I want this to be N, and I want this to be M. So to break it into columns, I had to do how many? Yeah. 6, which in general terms, in terms of M, is M minus 1. So then to break each one of these, where this is N, this is 1. How many breaks do I have to do to break this individual column? N minus 1. So now I've got all these individual pieces of chocolate. I have to handle the rest of them. How many total? 7, which is 7 is 1, 2, 3, 4, 5, 6, 7. It's M. So we're looking at the case where M is 7 and N is 4. Okay, so I am gonna give it away. It's going to look something like M minus 1 plus M times N minus 1.
again, if you have broken it differently, so in this case, we broke it into columns, and I know we're out of time too. We broke it into columns first, and then we break off the individual pieces for the quote unquote rows. And to do that, then we got m minus 1 plus m times n minus 1. And if you had chosen to break it differently, so let's say, like what I did when I first thought of this, I broke it by rows first. And then I have to break each row into its 7 individual pieces. And so to break the rows, I did n minus 1. And then I broke into the individual pieces across the columns. And so I did this n times, because I got n rows, then m minus 1. So these are equivalent with swapping n and m. Okay, that's it for now. I will see you on Tuesday where we will begin the algorithm analysis unit. I'll let you know the due date of the packet, but keep working on it. If you've got questions on the chocolate bar, come see me. I've got office hours. It will be Monday, 1 to 3.